Consider the graph of x squared plus xy plus y squared is equal to 27. Part A, we want to find y prime. So we want to find the derivative of y. And in this case, since our equation is in terms of both x and y, when we write find y prime, that really means we want to find dy dx. Those are two notations that communicate the same thing. Now, the equation that we've been given is an implicit equation, and we know that because we have not solved explicitly for one of the variables. In other words, you don't see one of the variables completely alone. So because it's an implicit equation, we need to use implicit differentiation. So we're going to take the derivative of the left side with respect to x. So everything on the left, we'll take the derivative of that, and then everything on the right. So taking the derivative of both sides of the equation is always our first step. And again, some of you may not be writing this step out anymore, which is completely fine. I'm just going to put it here for clarity. And then we see that we have three terms being added to one another. So we know the sum rule says we will take the derivative of each of those terms separately and then add the results. So it would look like this if we were using proper notation for each step. But once again, if this is a step that you're not writing out, that is completely fine. If you're past this and you understand the notation, that's great. Now on the right-hand side, the derivative of 27 is just 0 because it's a constant. Back to the left side, so we need to take the derivative of these three terms. So the derivative of x squared will just be 2x. And then we have to remember that the derivative of x times y requires the product rule because we are multiplying x times y. We have a product here. So we will take the first factor, which is x, and multiply it by the derivative of y. But the derivative of y with respect to x is dy dx, plus the second factor, which is just y, and then multiply that by the derivative of x, which is just 1. Then the derivative of y squared will be 2y, but remember you have to chain on dy dx because of the chain rule. And then at this point, we need to solve for dy dx, and you'll notice that there are two terms that contain a dy dx, and we will want to leave those terms on this side of the equation so we can factor out a dy dx. And I like to do this kind of all in one step. So I'm going to go ahead and factor out a dy dx from the two terms that I have highlighted in blue. But the other two terms do not contain a dy dx. So I'm going to go ahead and subtract those terms to the other side. So that would be a negative 2x minus y. Now we can finish this up by solving for dy dx by dividing by the quantity x plus 2y. So this gives negative 2x minus y, all divided by x plus 2y. And this would be our answer for part A, when it asked us to find y prime. Now this is our general derivative. You'll notice it is in terms of both x and y, which is not surprising since the original equation was an implicit equation. And this is the general equation for the slope. That's what the derivative is, right? The slope of the tangent line. So this is the general equation for the slope at any point on the curve. Now you'll notice this particular equation, the original equation, the x squared plus xy plus y squared equals 27, that created a rotated ellipse that I went ahead and graphed for you here in Desmos. And so now part B is asking us to find the points on the graph where there might be a vertical tangent line, okay, using implicit differentiation. So we've already done the implicit differentiation part where we have computed the derivative. So now we're just going to do a little analysis on this derivative. In order to have a vertical tangent line, that means we have a place where the slope is undefined. And remember, that's because a vertical line has an undefined slope. So a vertical tangent line means the slope would be undefined. So if we take our derivative from part A dy dx is equal to negative 2x minus y, all divided by x plus 2y. And we're wondering where this derivative might be undefined, since the derivative, remember, is the slope. We know that that would only happen when the denominator was equal to 0. So if we take that denominator and we set the denominator equal to 0, because we know that division by 0 is undefined, then we'll have x plus 2y is equal to 0. So this is essentially a relationship, an equation. It relates x and y. And we're really trying to solve for the point where the tangent line is 0. So if you can think of this sort of like a system of equations where we have one equation here in terms of x and y, we need a second equation that is in terms of x and y, so we can then solve the system of equations and solve for a very specific x and y value. So let me take a time out here just for a second and remind you about systems of equations. In the past, you would have seen a system of equation maybe in your college algebra class. Okay, and you might have seen a system of equations that looks like this, something like, 2x plus 3y is equal to 5, and maybe 4x, minus y is equal to 8, something like that, where you have two equations with the same unknowns. This is called a system of equations. And typically in the previous math classes, you solve systems that look like this. This happens to be a linear system of equations. And so when you're solving the system, you're essentially looking for the intersection point where the two lines intersect. And it doesn't have to be linear. We could certainly have one of these be squared, and then maybe now we have the intersection of a parabola and a line where you have a possibility of more than one intersection. But the point is, a system of equations is going to be several equations that have the same unknowns. And so we're searching for their intersection points. And to solve a system, there's two algebraic ways of solving. You can solve it by substitution, or you can solve by elimination. And that's really what we need to know, the skill set that we need to help us solve this problem, is we have to remember what a system of equations is and how to solve it algebraically. So we have this equation. I'm going to put a box around it right now. We have x plus 2y is equal to 0. Because I'm not sure what we're going to do with that yet, but I'm recognizing that it has two unknowns. It has two variables. So I need to hunt for another equation that also relates x and y. I need a second equation that relates x and y. And I don't want to use the derivative here because the derivative has the dy dx. We're not interested in an equation that has dy dx. We just want an equation that contains x and y that gives us the relationship between x and y. And the only other equation that we have that would do that would be the original implicit equation we were given, which is the equation for the ellipse. All of the points that end up lying on this rotated ellipse. So our second equation, if we go back to the original equation, that's going to essentially be the equation that we're going to use as our second equation in this system of equations. So the original equation of the ellipse was x squared plus xy plus y squared is equal to 27. And this is going to be the second equation in our system of equations. So we have a system of equations now that we're trying to solve, and we're going to solve that using either substitution or elimination. So in this case, it's going to be easiest to take our first equation, x plus 2y equals 0, and solve for one of our variables. And it's a lot easier to go ahead and solve for x by subtracting 2y. So we'll have x is equal to negative 2y. And then we'll do a little substitution into our second equation. So everywhere we have an x, it's going to become 2y. So we're solving this using substitution. So negative 2y, the quantity squared, and then plus negative 2y times y, plus y squared is equal to 27. This is what we'll get once we do our substitution. So this is definitely one of those problems where it's going to require us to really dig back into our tool belt with our algebra skills and bring out some of those old tools. And in this case, it's how to solve a system of equations. So now we have an equation all in terms of one variable, And so if we simplify, we'll end up with 4y squared minus 2y squared plus y squared equals 27. And this is a pretty simple equation that we can go ahead and finish and solve. So we'll end up with 3y squared is equal to 27. Divide by 3, so y squared is equal to 9. And then square root both sides. So remembering that when we're taking the square root, in this case, we'll end up with both a plus and a minus 3. So the direction said find the point or points on the graph where a vertical tangent line exists. So we haven't found the full coordinate yet. We've only found the y value. So we really need to find an ordered pair. We need to find the x value as well. So again, kind of thinking back here to what you did in the previous class when you were solving systems of equations that look like this. Once you found one variable, you had to substitute that variable back in to one of the equations to find the other, because we were looking for the point of intersection. And that's exactly what we're going to do here. So we have y, and we need to substitute it back to find x. And if you take a look at your equations, you have two options. You could substitute it back into this equation, the x plus 2y equals 0, or you could substitute it back into the original equation, because these were the two equations that we were using for our system of equations. And of course, we want to take the easiest route, and it would be much easier to plug that y value back into the x plus 2y equals 0 equation. And that's what we'll do to finish this. So finishing this off, sorry for all my arrows. So if we were to have x plus 2y equals 0, but we'll go ahead and substitute in positive 3 for y, then that's going to give us x is equal to negative 6. So we have one of our points. When x is negative 6, our y value is 3. But there was a second y value. So if we substitute again back into the equation x plus 2y equals 0. So x plus 2 times negative 3 equals 0. And then that would be x minus 6 equals 0. So x equals positive 6. So it looks like there are going to be 2 points. The second point would be when x is positive 6, y is negative 3. And it looks to be 2 points where a tangent line would be vertical. And the reason I gave you a graph here is so that we could look back at our graph and check and see if this looks right. So back to the graph, let's look at negative 6, 3. So if we go to negative 6, 3, that's right here on this ellipse, and sure enough, it does look like our tangent line would be vertical there, which is great. And then the other point was positive 6, negative 3, and you can see there as well would be another point, a second point on the ellipse where the tangent line's vertical. So the graph confirms that our answers are correct. All right, we're almost there. Part C, find the point or points on the graph where we have a horizontal tangent. So similar line of thinking here. In fact, I would encourage you to go ahead and see if you could solve part C on your own. Pause the video and then, fast forward and see if your answer is correct. Because this is going to be solved very similarly to how we solved B. So now, if we're looking for a horizontal tangent line this time, we don't want the slope to be undefined, but now we want the slope to equal 0. So once again, we'll go back to our derivative. dy dx is equal to negative 2x minus y, all divided by x plus 2y. But this time, if we want this entire fraction to equal 0, then that would only happen when the numerator is equal to 0. So we're going to set the numerator equal to 0 this time, which gives us negative 2x minus y is equal to 0. So once again, this is going to be our first equation in our system of equations, and we're going to need that second equation again. So we'll utilize the original equation just like we did in part B and create our system of equations. So I'm just putting boxes around these equations, not because they're your final answer, but because I want you just to see these are the two equations that we're using as our system of equations. Now let's go ahead and take the equation from these two that looks easier or simpler, which would be the top equation here. Negative 2x minus y equals 0, and we'll solve for one of our variables. I will go ahead and add y to the other side. So negative 2x is equal to positive y. And this is the equation that I will substitute into the original, the x squared plus xy plus y squared equals 27. Now let's substitute. X squared plus x times y, but y is negative 2x, plus y squared, so again, the quantity negative 2x squared is equal to 27. Simplifying gives x squared minus 2x squared plus 4x squared equals 27. That'll be 3x squared is equal to 27. So x squared is equal to 9. So x is equal to plus or minus 3. So again, right now it looks like we have two coordinates, one where x is equal to 3, and the second coordinate where x is equal to negative 3. But we still need to find the points, so we need to find the corresponding y value. So again, we would do substitution. And you can substitute back into either of the equations you used for your system. And it's always nicer to go to the simpler looking one, which would be the y is equal to negative 2x. So we have the x value, we just need the y value. So y is equal to negative 2 times positive 3. So again, that would give us negative 6. And then same thing, if we substitute in negative 3 for x, we would get positive 6. So it looks like we're getting two different coordinates, 2 points on the original ellipse where the tangent lines appear to be horizontal. Let's go back to the original graph and just verify that this looks right. So back to our ellipse here. If we go to 3, negative 6, that would be down here. Sure enough, our tangent line looks horizontal there. And it does also here at negative 3, positive 6. You survived. Good work.